values. And we can develop the sequence for 2 to 10, or we could develop the sequence for 2 to 100, and Mathematica will very quickly go in and calculate all 100 values, or the first, what we might say is 98 values of this sequence, all the way up to the case for n equal to 100, which is given by 10,000 divided by 999, or 9,999. All right. Now, one of the things this doesn't afford us to do, though, is to go in and find a specific value of the sequence. So if we consider finding a specific value of the sequence, we might change things up here slightly. Instead of defining my function inside of the table here for the terms of the sequence explicitly in terms of n, what I might do is go out and define this argument given here as a function of n, right, previous to the table argument. Now, in Mathematica, to define a function, you are going to adopt some function notation. Now, in Mathematica, functions are denoted using brackets versus parentheses. Parentheses are strictly grouping symbols used in mathematical calculation versus defining of statements. So we are going to define function f of n here, and actually in Mathematica, when defining a function symbolically, the independent variable inside the function notation is going to be followed by an underscore. And what that tells Mathematica to do is to hold that value of n as the independent variable inside the function. Now, to actually define the function, I could say that this is going to equal our quantity, n divided by 2, or n squared divided by n squared minus 1, right? And you'll notice if I hit enter now, it will actually state what is function f of n, right, in its symbolic form, n squared over n squared minus 1, and notice it does do some rearranging of terms in that denominator, but it also states out our series, or our sequence here, our sequence for the case of n equal to 2 all the way up to 100 for this function. Now, in this notation here, I did make function f of n equal to this. We did, in a sense, set this symbolic notation f of n equal to this symbolic calculation. We can also, if we want to avoid having this output show, we can actually make that a set delayed argument and put a colon equals in the notation here in Mathematica. By making that a colon equals, what this will do is it will set function f of n equal to this argument of n, but it's not going to it holds it in the background in a sense until that function is actually called up on in some other calculation like f of n here. So you'll notice this time around, if I hit shift enter, all I get is the sequence of arguments versus the actual statement of the function followed by the sequence. Now this is convenient because what I can do, right, once I have stated function f of n, we might go ahead and simplify this again. We'll drop this down to 10 so we don't get a crazy argument, crazy number here. But I can also call out function f at different values. I might be interested in what is f at the 255th term. Right? Now when I hit enter, I do get again my sequence from the 2nd to the 10th term, but it also gives me the format for the 255th term. Right? If you're someone like me, I also like to add other variables into my arguments here. For instance, always having to come down and change these lower bounds inside of my set might be a little troublesome at times, or cumbersome at times as I get into formula. So I might call those out as values a and b, and come back up here into earlier into my program and define A to be equal to maybe the number 2 and B to be equal to the number 10. And again, we'll see here when I hit enter, it makes that calculation. Right? If I wanted to plot this sequence on an on an n f of n coordinate plane in a two-dimensional system, what I could do then is come along and make a table to begin with of a series of coordinates. Now, coordinates in Mathematica are represented using a grouping, braces as grouping symbols. And I'm going to want to form the coordinates n and f of n, right, as to represent the values of the sequence in two-dimensional space. N highlighting the index and f of n highlighting the value of the sequence for that nth index. Now again, we might consider this table of values from values of n over values from a to b, and here you can see where that use of a to b above, right, allows me to call out a and b in the table without having to change it. And if I wanted to change these values, I could simply change it once up here above and it'll change all of them down below. But now if I hit enter, those will be the coordinates that we're going to plot in our plot here. And the actual plot function that we're going to use, here, folks, pardon me, I've been lecturing all day, so my throat is getting a little dry. What we're going to actually make is a list plot. All right? We're going to make a list plot for this table of values that we formed above. Now, I could just copy and paste that table down into my list plot here, but what I'm actually going to go ahead and do, and this is what's convenient in my Mathematica, is I could actually call this value for the table out as a variable. I might call this table out as the variable value t sub 1, representing table 1. And down here in my list plot, instead of actually copying and pasting that table argument down into the list plot, I can now just bring down t sub 1, or t of 1. That list plot then is going to have to occur, right? We're going to want to plot over values of x, or well, in this case, n, where we're going to consider those values of n occurring from a to b. And I believe now when I hit enter, oh, hold on here. Let me double check. Oh, you know what? In a list plot, I don't have to state these bounds. I just have to state my table. That's my issue. There we go. We get a nice picture. All right. List plots don't need any bounds. It actually uses the values seen in the table or in the coordinates to mark its bounds. Now, you can adjust the range if necessary. Here we might be interested in adjusting our range. You could always come in and follow up T1 with some plot commands, such as plot range. You could have a range that is filled in automatically. Or make it automatic is the command. And in fact, we could come over and search plot range and get an idea of what are some of the options there, right? If we click in here, we can see we can set plot range to all or automatic or full, and they all have different options available. You know, what I like to sometimes do is actually call out my range. I could call out a range from 0 to maybe 2 in this case and hit enter, shift enter, and it'll plot out that range along our y-axis from 0 to 2, right? As I can see, that does kind of well, it certainly does change how these dots relate to one another. If I wanted to, I could consider looking at just the plot range from 1 to perhaps the value of 2, and certainly we see a different, right, illustration of that behavior, but nonetheless the same in its description, just different values along the range, right? Or maybe even bring that down to 1.5, and we really can emphasize the change here in the terms of the sequence as n progresses forward. When working with non-alternating series, sequences that are always going to have terms greater than 0, another convenient plot range to set is the range from 0 to automatic. In that particular case, it always starts at 0 and automatically sets the upper bound. Yeah, that's a good way to call out your plot range. I'm trying to think what are some other things we can do here. But that does present a plot of this data, or in a sense of the sequence. Oh, what we might want to add to this plot are some labels on our axes. If you notice, our axes don't have any labels. So in a plot, you can always change or label the axes with the command axis label. Notice here, this is all just inside of the list plot command, where we are plotting table 1 with that followed by some plot commands, and these plot commands can happen in any order. The first command being a command for plot range. And you'll notice I formatted this arrow. Now, where these arrows come from is it is a minus sign followed by a greater than symbol that I bring together in one stroke, or in two strokes without the space. Here to make this axis label a command, we are going to use the minus sign, and I am going to follow that with a greater than symbol but without the space, and what it produces is that arrow, right? And what we might label our axes here, the x-axis and the y-axis, right, would follow as this coordinate, but specifically we might call out the x-axis or the horizontal axis as the axis for n, and I'm going to use some parentheses here, which tells Mathematica to interpret these values as text values versus actually function commands. If I was to put in f of n using brackets here instead, what it would actually label out potentially is this argument up here. You'll notice by putting it in parentheses, I actually get, we'll see here, text format for those labels. And there we can see the labels n and f of n appear in our graph. Right? If I wanted to change the color, right, there's an option for that. That is plot style, right? Where again, with that right arrow, I could call out a color for this plot. Maybe I want the color red. Right? And it should make my plot in red. I'll go back to black. For some of you, you might be interested in saying, well, how do I actually plot then the function through this? How I obtained the function through this graph earlier was I made another plot, just known as a plot. Plot is a way to plot functions two-dimensionally in Mathematica. And what we could just plot is function f of n, right, which is going to treat it more in a continuous manner as opposed to the discrete plot that we see in a list plot. And here we do have to call out a range of, or a domain of independent values. So let's say where this is going to occur over values of n that starts at a and continues off to b. Now when I hit enter, you'll see that that plot does fall below, right? But it does not fall on top of the scatter, or the dot plot that we have above. To actually get these two plots to form in one graph alone, what we can do is go back, and as I've highlighted with the table, is I'm going to go ahead and call out these plots as their own values. I'm going to set delay the list plot to value P1, and I'm going to set delay the plot to P2 in value. Right? Now when I hit enter, you'll see that I don't get any plots that show up. What I have to do to combine the two plots is use what we call the show command. If I bring up the show command and inside its argument put in P1 for plot 1 and P2 for plot 2 and now hit enter, it combines those two plots into one. Now one drawback you will happen to see here is that it's leaving out a bit of A. It's leaving out our A value here. Well, I should say it's starting at A equal to 2, but it's not quite graphing all the way up there. We don't have any domain limitations up there. Maybe I adjust this slightly. Instead, maybe we make this the location A minus 1. Right? Do we get a nice looking? Yeah, there we go. We get a slightly nicer looking graph. One other thing to point out is if we want, well, first of all, in this show window, the order of these plots is somewhat important. The actual plot options that it uses comes from the very first plot that we use in the show command. For instance, here it is grabbing the commands from the list plot, such as the range, the axis labels, and the plot style there for black from this list plot. If I wanted to make plot 2 a certain color, I certainly would have to come down here and change its plot style to perhaps the graph. Maybe we make it red, and we can see there we get that function plotted out in red. But if I want to apply a command to the combination of graphs, I can also do that for many commands. For instance, I could change the size of this plot and consider the image size to be maybe small. If I want to put it into a document and it needs to be rather small, I can make it small, or maybe I make it large so that it shows up nicely. Right? It's easier to see, and you can certainly get a larger graph there. All right. But yeah, folks, this is the first quick little lesson I wanted to give you on just working within Mathematica and using it to actually help us explore the values of sequences. Hopefully I've given you some things to start off with in terms of just beginning to develop one of your first programs here in the study of sequences. And maybe they'll figure out some way of sharing this with you so that you could just explore around with this and at least be able to have this program to run on your own outside of class. So, folks, I'll stop there, but hopefully this helped you out. Like I said, it's just another lesson that I'm able to do here by giving you some presentations online, and it's something that you might find useful for both this class and for future classes, and not just math classes, science classes, and not just future in terms of Calculus 3, but in all your future studies. Folks, Mathematica is a program that is just widely used across universities and widely used across industry. So being familiar with it is certainly something that you're going to want to get a jump on here. And now we have a bit of a way of doing that. So see you folks in the next video, and I'll hopefully get back here and show you some more. Later. Hey there, folks. As I went back and watched over the last video, I realized there's maybe one or two more things I want to show you, or at least kind of clarify with respect to, first of all, these plots, and then just go a little further with sequences and show you on here that some of the capabilities in Mathematica and some of how to use those capabilities. First thing off, just to clarify in these graphs, some of these plot commands have no effect down here in the show command. If I was to try to make a plot style, I believe down here, right? For instance, maybe magenta, right? That I don't think is going to have any effect, right? That plot style is only plot specific. It's not actually capable to perform in show. Again, with respect to order of these plots, the plot commands that are able to come down here and be used in show will actually, if not brought down here and are actually used up here in the individual plots themselves, such as the plot range or the axis label, those will be, well, I should say again, the first plot used up in the show command here is what's going to dictate those commands. For instance, that image size command that I removed there can happen in either of these statements. I could have this produce an image size of, maybe we make this one small, and I could say this one has an image size of large. And again, I'm going to go over here and show you that this is one of the reasons why we set delay items, is not always do I want to have every command appear down below here. As you had noticed before, those list plots and the plot didn't appear, just the combination of the two with the show command. by removing the colon and just setting these plots equal to these arguments, when I hit enter, it's going to go ahead and show these two plots as well as what we get from the combination and show. So if I hit shift enter, you can see here what I do get is, again, that's what sequence that we're plotting. I do get the list plot, and again, because we set the image size in that case to small, we do get a small plot plotted. Whereas in the second plot, the plot of our function, what I've been calling the plot, it has the red plot. It has an image size that is large. Now, when it comes to combining the two in the show plot, the image size that we actually get in the show plot is small because plot 1 is what occurs first in that show. If we were to change the order of these plots, it's going to apply the plot options for P2, and they will override any similar plot options in P1. I believe if I hit enter, again, we get plot 1, we get plot 2, and now this time around, the show plot, because plot 2 is first in the order, is now large. That image size of large overriding this image size of small in our first plot. Certainly the colors do not change. We also do notice a plot range difference. Certainly we get a different plot range. If I was to change that order back to P1 and P2, again we get that smaller plot, and also a different plot range. If I was to change this size to large, we would now have a large plot for all of our plots, plot range being from 0 to 1.4, that's 0 to automatic setting, right, that we set here. Whereas if I now reorder that as P2 comma P1 and plot the two together, P2's plot range is going to take default, right, in terms of its illustration. So we end up starting at what it thinks is appropriate. I think it automatically goes with its settings if we don't set anything specific. Now I do again like P1 versus P2 first. So I'll go back to those plots. And again, this is why we have the set delay, is because not every time do we want both of these plots appearing before the combination of the two, so we can set those back equal to using the colon, making a set equal combination, and get back to our original plot here, folks. So that's one thing I wanted to show you, I think, to clarify on. I don't think that was so clear the first time around with this show command. And then the other thing I wanted to show you was limits. You can do limits on Mathematica here. Again, I'm going to look up limits here. Again, this is where the command window comes in. If you were interested in, well, how do I calculate a limit on Mathematica? I come in over here and look up limits, and it says, yeah, you got, first thing that comes up is a limit function. It's a built-in symbol, or what we call a function here. And if I click on it, it's going to show me some of the statements I can make for limits. And what we're going to be interested in is this one variable limit. But there are cases for what we think of as being multivariable limits. As you go on to Calc 3, you will be looking at multivariable limits. In this case, we are going to be looking at a limit. Limit is the command, not limits. All functions in Mathematica involve brackets for the commands of the function. Here we are going to want to call out our function f as f of n. Right, we've declared that as the first line in our statement. And as it highlights, we are going to want to make note of what is the variable in the limit, what is changing, or what is the independent value in our limit of the function, and that's going to be n. And as it shows us, we are going to be using that right arrow, and again, that's made with the minus sign followed by a greater than symbol without the space. We'll make the right arrow. And then we are going to want to head towards infinity, where I do believe we can just type in the word infinity. Now let me double check. Again, this is where this... Yep, I believe we can just use the word infinity. There is a symbol that we can bring up for infinity. I don't know if we're not going to worry about symbology yet today, or some of the other simple symbol commands. Oh, and I see why it's not. Now notice here, Mathematica, it treats variables when it recognizes what it thinks as a variable that it has not ran before in the program. You'll notice that it hasn't done this with any of the other variables, is it turns the variable blue. So right there, because I misspelled infinity, it's treating it as a variable, where if I go actually and correctly spell the word infinity, now you can see that it's treating it as a bit of a command. Right? And in fact, we can go down below and see that it recognizes it as the infinity command. So here we're going to find the limit for f of n as n heads to infinity. And we can certainly see that it has a particular type of behavior to it. If we were to be a little suspectful, and in fact we can start to see that if we were to increase our bounds up towards 100, right? This is the graph we get. It certainly looks like it's approaching the value of 1. And if we scroll down, here's our result for that value of the limit. The limit does happen to equal the value of 1. If I wanted to actually make it so you could recognize that as the result, this is where the print command comes in, right? In fact, what I could say here, we'll go ahead and call this limit a delayed value, right? And we'll come in and maybe say something like print, right? Print is a way of being able to print a string of text. We're going to use parentheses to say this string, and we might just print the line, the limit of the sequence is space, and then we'll follow that with comma, L1. And what this will do is print the statement, the limit of the sequence is, followed by a space, and then it will give us what the actual value of the limit is. Now, you'll notice when I hit enter, again we get, well, let's change that. Let's drop that back down to 10 so we get some nice picture. Right? Here's our sequence. Here's our illustration of that sequence. Certainly it appears to be heading towards the value of 1, and as we've stated down below here, the limit of the sequence is 1. All right, and this limit function doesn't only work for sequences, it works for all functions. And in fact, Mathematica is not looking at f of n here as any sort of sequence. It is really interpreting it as a function of n. It's not until we actually look at it as a table of values, either as this table f of n or this table n comma f of n, this coordinates in our plot, is when we're taking that, what we might think of as continuous behavior given by function f, and illustrating it in a more of a discrete aspect inside of the table as a finite number of values, as plots in a plot. All right. So folks, again, I wanted to show you a little bit more here with respect to sequences, and kind of make sure that this study was thorough on Mathematica and showing you some of the optionality here, what we're able to do in the system. And I think I am happy with that. So again, folks, I'll be back with more. Hang in there.